Hi again, I'm Neil. This chapter is all about, well, this guy, Isaac Newton, born on Christmas Day, 1642, in Woolsthorpe, England. Arguably the greatest scientific mind to have ever lived. Isaac Newton revolutionized our understanding of the natural world and how things work and why they work the way they do. He derived, well, many things. In this chapter, we'll focus on the equations of motion. And in subsequent chapters, we'll talk about other things such as gravity, for example, universal gravitation. But Isaac Newton, he spent much of his life, by nothing more than trial and error, deriving the laws that govern the working of the physical world. So if we were to consider the space program, here's a space shuttle. It's got his fingerprints all over it. The foundation for the space program was laid in large part by the work of Isaac Newton, centuries ago as a very young man in his 20s. He was describing equations and deriving equations that governs rocket motion. Newtonian mechanics is what they now call it in honor of Sir Isaac Newton. Now, in this chapter, I'll pull up the chapter here, we consider the forces acting as Newton did, multiple forces acting in many directions, 2 and 3 dimensions, on one object or a system of objects. And we derive equations to understand and predict the behavior of how objects will move or not move. Will they accelerate? Will they move at a constant velocity? Will they not move at all? All of these things are dealt with in this chapter on force and motion. Now, if we were to scroll down, we can get an idea of the content of this chapter. The basic definitions of what a force is, what a normal force is. It's a reaction to the weight of an object. That's one of Newton's laws, actually, one of his 3 laws of motion, his 3rd law, as a matter of fact. For every action is an equal and opposite reaction. So the normal force is the reaction force to an object's weight. So as we set the stage for deriving the equations of motion, we look at the forces acting in each direction, both the x and the y. They are independent of each other. They are linked by certain parameters, but they are independent of each other. We talk about friction and the origins of friction. In some cases, friction is absolutely necessary. For example, the friction between the tires of a car and a roadway. Friction is necessary to keep the car on the road. But in other things, you want to minimize friction. For example, the working parts of an engine of a car, for example. This is why we change the oil in a car, to make sure that the chemical composition hasn't broken down over time upon exposure to extreme temperatures in the engine of a car. The lubrication properties diminishes over time, so you change the oil in your car to reduce friction and hence the wear and tear of the metal parts of your car, in the engine, for example. So we talk about friction and the difference between static friction and kinetic friction, the coefficient of friction, which is essentially a measure of the slipperiness, I suppose, of an object upon another, for a lack of a better way of saying it. We talk about drag coefficient. Airplanes flying through the atmosphere, they deal with a lot of drag, and the consequences of this drag force determines fuel consumption, for example. So it's important things to consider. We look at the forces acting in vertical motion. One of the examples that's dealt with in this chapter deals with something as simple as rainfall. And the average person, you may not realize it, but an average rainfall, the velocity of which a single raindrop would hit the earth falling from a rain cloud, would be equivalent to a speeding bullet. It will kill you, I know, in certain terms. From a single rainfall, millions of people would die if they were exposed to, the water droplets. If were not for the friction due to the atmosphere, the air molecules slowing down the speed of the raindrop. So that's actually one of the examples, which I think is quite interesting. That's dealt with. We calculate the speed of the drop with and without friction. You will see that there is a significant difference here. And our very lives, we owe the resistance of the atmosphere for keeping us from certain death. So, as we continue on down in this chapter, now we look at objects that are much larger than a raindrop, objects that are exposed to multiple forces, maybe friction, normal force, weight, or some component thereof of its weight. And we write down Newton's equations and we solve for a variety of properties, maybe acceleration of the object, mass of the object, etc. Multiple objects tethered maybe by a cord over a pulley, as this problem deals with. We apply Newton's equations independently to each object, but each object, since they're tethered by the same rope, they've got a few things in common as long as the rope remains taut. The tension in the rope and the acceleration of each object, well, they share those things in common. So that's the unifying parameter, or parameters, in a solution to the equation. So we do many examples to such an end. On one of my trips to the Far East, this is the bullet train in Japan, the Shinkansen. So we work on an example of the forces acting if you were to ever make your way out to Japan. The sushi is fantastic, but the bullet train is also a lot of fun. And so we work on an example of calculating the sum of the forces acting if you were riding on the bullet train. Consider things such as the friction between the track and the bottom of the train, the rails itself. Another example is in the far north of Sweden, close to the Arctic Circle. In wintertime, I decided to try my hand at dog sledding. It didn't go so well, but it was a lot of fun. I'll probably never do that ever again. Never been so cold in my life. But the sled that's being pulled by these sled dogs actually glides on a very thin layer of water that comes from the friction of the melted ice and the snow that's on this frozen lake. So the frictional forces acting as these dogs are pulling away over here is considered as a real-life example on the calculations of the tension in the guidelines that are used to keep the dogs at bay. So it's a real-life example of if you ever tried your hands at dog mushing, what can be expected. There's another problem in this chapter that took me to the exact opposite end of the earth, from one pole to the other. In the previous example here, I was close to the North Pole in the far Arctic, far north of Sweden, and this is the other pole of the planet, from pole to pole in these two examples. This is Antarctica, one of my more adventurous trips. I was mountaineering, and many of these peaks have never been climbed before. They're uncharted, they have no names. These are my climbing partners from Liechtenstein. And you can probably see back here, it's a little boat back there. I don't know if it's possible to see it, but that's the Plantius, a Dutch expedition vessel. And that got me all the way down to the bottom of the earth. That's me right there in the middle. And so we're roped up in case we fall off, and by we I mean me. There's some chance of being rescued. So this diagram shows Newton's laws. If the unfortunate situation were to arise where one of us did fall off the mountain, we are to be saved from certain death, quite honestly, falling off into the semi-frozen Arctic Ocean. There's a lot of ice over there, and it's very, very cold, not to mention there are killer orca whales lurking around. So this is an example of solving problems dealing with the equations of motion for multiple objects acting. And we apply Newton's laws as well, very simply to circular motion, not just linear motion. Not a great detail of work has been done in this particular chapter in circular motion. That comes in a whole separate chapter all by itself. But suffice to say that objects that are not moving linearly in a straight line must be undergoing some form of curvature, of angular motion. And there are two different components of acceleration to consider if the motion is not linear. And so we can talk later on about the radial acceleration, or the straight line acceleration, and the tangential acceleration, which, as the name implies, acts at a tangent to the curvature of the motion. This would be right about here. So we've got a radial acceleration here and a tangential acceleration. So anything that's not moving in a straight line has multiple forces acting on it, and the net force is a consequence of two components of acceleration. One acting from the point on the periphery of the circle towards the center of the circle, and the acceleration acting in a tangent. So the addition of those two components is used in the calculation of what's called the centripetal force, the force that's keeping the object moving in a curved path. Much more on centripetal forces later on. There's an example of a fighter pilot here moving in a vertical circle, doing a loop-de-loop. And if you've ever watched movies and such things, you probably noticed that fighter pilots, they wear masks. The mask is supplies oxygen. This is so they don't pass out when they're doing vertical loops. If you accelerate beyond a certain number of G's, the human physiology is not made for that, and your body can quite literally accelerate faster than your heart can pump blood through your arteries to get to your brain, and you can pass out from a lack of oxygen to your brain. So we do a really interesting example here of the calculation of where in this vertical loop is a pilot experiencing the greatest G-forces, where he or she is most likely to pass out. It might not be what you think, and you'd have to go read the chapter to find out where it is. And this is the actual calculations for it. And as with every chapter, there are some additional chapters at the end, additional problems at the end of this chapter that you can work on as well. So it's quite detailed, and some very significant things are derived about the natural world and why things work the way they do. And as with all chapters, I've used my travels around the world for real-life examples of the physics at work. So I certainly hope you find that interesting. Thank you.